If you don't know classification metrics like precision, recall, and F1 score, trust me, you'll want to keep watching. Using what is known as binary classification, we can detect if a tumor is cancerous, or if a credit card transaction is fraudulent, or any model that you want to make. But since none of these models will be perfect, we need metrics. Now, there are many different metrics we can use for this, and trust me, it is worth understanding them all. Employers need you to know this. I'll explain all of them clearly and concisely, and we'll implement each of them in Python. That's how to really show that you know these things. This stuff can be a little bit confusing at first. I'm going to explain it as best as I possibly can, so let's get started. First thing we're going to do is implement a binary classification model using logistic regression. If you already know how to do that, just skip to the section down below where we implement our first metric. We'll be using the credit card fraud detection dataset from Kaggle. Make sure you have that CSV downloaded into your environment. We load the dataset into a data frame with import pandas as pd, df is equal to pd.read CSV, creditcard.csv, and we output df.head. This gives a data frame of credit card transactions with a time column, V1 all the way up until V28, which are just hidden PCA reduced data, and amount is the dollar amount of the transaction, and the most important thing is the output variable class. It is 0 if it is not fraud, and 1 if it is fraud. As we can see, the first 5 results are all not fraud. This will actually be very common, as df subclass value counts. That shows that there are 284,315 not frauds and only 492 frauds. It is a very imbalanced data set. We wish to train a machine learning model that can accurately predict whether it is not fraud or fraud. To do that, we will look at all of the other columns of the transaction and train with logistic regression supervised learning. We'll start by shuffling the rows of the data frame with df is equal to df.sample, track equals 1, random state equals 1, so we get the same results every time. Then we do df is equal to df.reset index, and we specify that drop is equal to true. Again, we'll output df.head. The rows are indeed shuffled. Now we'll convert the data frame to a numpy array with as numpy df.toNumpy and get this index value, which is equal to the integer of the length of as numpy. That's how many rows we have, and then we'll multiply it by 0.92. A slightly unconventional split. This will make 92% of the data for train and the remaining 8% left for test. We'll get our input training matrix xtrain, and our output training vector ytrain of outputs is equal to as numpy, where we index this all the way up until index, only the rows from the beginning to index, colon, -1, which says we want all of the columns other than the last column. That makes sense for xtrain because we want all of these columns other than the last one. And so for ytrain, we set that to be the same thing, so we copy that and paste that over there, except we remove the colon because we want only the last column. Now to get the test input matrix and the test output vector, we're essentially going to copy and paste this line and just move around this colon here from index onward, and same thing over here, test and test. We can look at the shapes of all of these different arrays. I'm just going to paste this in here. xtrain.shape, ytrain.shape, xtest.shape, and ytest.shape. We'll see that 262,022 examples fell in the train. For the inputs, we have 30 columns, and for the outputs, we just have whether they're not fraud or fraud. And the same thing for test, except only 22,785 examples. For making machine learning models, it's common practice to do some sort of pre-processing or scaling so that every column in your input is roughly the same sort of values as the other ones. A simple but not necessarily the best fix to this is to do standard scaling across every column. So we will do from sklearn.preprocessing import standard scaler. We'll make a scaler equal to the standard scaler .fit xtrain, and then we'll set xtrain equal to the scaler .transform of xtrain, and we'll set xtest equal to the scaler .transform of xtest. Now if we look at the first row of xtest, which is xtest sub 0, we'll see that all of the values are roughly the same. Now we can train our logistic regression model. So we'll do from sklearn.linear_model import logistic regression. We'll make model equal to a logistic regression, and then we'll fit that, passing it xtrain and ytrain. We can get our predictions for the test set with test_predictions is equal to model.predict, passing it the input matrix xtest. If we look at the pd.value counts of test predictions, we'll see that we have 22,757 predictions of not fraud and 28 predictions of fraud. We start with easily easily the most important metric there is, which is a confusion matrix. It shows the 4 possible scenarios. We'll see from sklearn.metrics, import confusion matrix. And to display it well, we can import the confusion matrix display class. We make a variable cm equal to a confusion matrix, and we need to pass this the observed values y_test and what our predictions were test_predictions. We also set the labels equal to just 0 and 1, and then we make the display for the confusion matrix equal to the confusion matrix display, where we specify the confusion matrix is our variable cm, and the variables we want to display are display labels 0 is not fraud and 1 is fraud. Then we just do display.plot. Here's the 4 possible scenarios and the count of each. If we predict not fraud and the true label was not fraud, that means it was correct, and we got 22,741 of those correct. The other diagonal is the other ways we were correct, which is when we predicted fraud and the true label was a fraud as well. We have 20 of those. But there's also 24 examples where we were wrong. Here, we predicted a label which was not fraud, but these were actually fraud, and there was 16 of those. And here, in the top right, there's 8 cases where we predicted fraud, but these are not fraud. The following terminology is essential to understand. We have 4 different terms here. These are true negatives, these are true positives, these are false negatives, and these are false positives. Don't worry, I will explain each of them over and over again. We would say that we have 22,741 true negatives. It is true because we accurately predicted the class. It was predicted as not fraud, and it was not fraud. And it's a negative because we refer to the not fraud class as in the 0 or negative class. We would say we have 22,741 true negatives. Now, it is worth noting that we decided to call the not fraud class the negative class or the 0 class. That is a convention, and usually you say the thing that we're looking for is the positive class. You're really looking for fraud, and you're not looking for not fraud. It just makes more sense that way. So if in the top left those are true negatives, these 20 are true positives. It's true because we accurately predicted the class, it's predicted as fraud, and the true label was fraud, and it's positive because this is the positive class. So those were when we have it right, which is the trues. The other 2 spots here, these are the falses. It's where we got it wrong. And so these are called 16 false negatives. We apply the class label in that terminology to what we predicted and not what it actually was. And so these are 16 false negatives. 16 times we predicted that frauds were actually not frauds. False negatives. You might be able to guess that these 8 over here are called false positives. 8 times we predicted these not frauds were actually frauds. We said 8 times these are positives, but they were actually negatives. So just one more time because it's so important. 22,741 true negatives, 20 true positives, 16 false negatives, and 8 false positives. To really drill this in our heads, I'm going to add a text label here which shows all of them where the check marks are where we were correct and the X's were where we were wrong. One more time, true negative means it was negative and we predicted negative. False positive means we predicted positive, but it was actually negative. False negative means we predicted negative, but it was actually positive. And true positive means it is positive and we predicted positive. Right, right, wrong, and wrong. Those 4 numbers form the basis for every metric we're going to look at. We can get them with true negatives, false positives, false negatives, true positives is equal to cm.ravel. That's really just taking the values out of our confusion matrix. And I'm going to format and print a string showing all of them, which has the true negatives, false positives, false negatives, true positives with tn, fp, fn, tp, print s. We can see those numbers there. The first metric that most people look at is called accuracy. Accuracy is equal to true positives plus true negatives divided by true positives plus true negatives plus false positives plus false negatives. This looks complicated, but really this is all the things we got right divided by every single thing at all. So it just forms a percentage of what we got correct. To create a function that calculates this, it's very, very easy. We do define accuracy. We take true negatives, false positives, false negatives, and true positives, and we just return what it says above. True positives plus true negatives divided by all of those things. accuracy and then format that with the accuracy, and we can see that our accuracy in this example is 99.9%, which makes it seem very good, but we will see by looking at other metrics that it's not necessarily as good as it seems. This following metric surprisingly has 3 different names, which is very annoying. It is recall, which is the same thing as sensitivity, which really just means the true positive rate. All of those mean the same thing, which is simply the true positives divided by all of the positives. So this is the positives that we got right, and these are true positives, so what we got right, plus false negatives. Those are what we predicted as negative, but were actually positive. Correct positives over all of the positives will show us something interesting. We can calculate this function again very easily. I'm not going to write it out because it's pretty much the same thing every time. We define true positive rate, taking true negatives, false negatives, true positives, and we return the true positives divided by the true positives plus the false negatives. We can calculate our true positive rate by just calling that function and setting it into that variable, and we will see true positive rate is 0.555 repeating. That means that of all of the positive examples that were there, we incorrectly classified nearly half of them. Of all the positives, we only said 55% of them are actually predicted as positive, meaning the other 45% were false negatives. That is a big problem. Now, that other 45% is actually called something as well. That is a metric known as the false negative rate. And it's really exactly the same thing as the true positive rate, except we replace TP with Fn. These things are going to add up to 1, because this value is going to be the opposite, the other 45% there. I'm just going to copy and paste this in because it's essentially the same thing. We just changed TPR to FNR, and we changed that TP to FN, and we're going to calculate the false negative rate instead, and we see it is that other 45% right there. In practice, we don't really use the false negative rate. Usually we just calculate the recall / sensitivity / true positive rate, and you can see the other one if you wanted to eyeball it. Now, all those metrics were about the positives. We now do the analogous thing for the negatives. So we have this thing called specificity, which is also called the true negative rate. It's really analogous to what's above, the true positive rate, except it's with negatives. The true negatives divided by all of the negatives, which is true negatives, plus the false positives, which are what we thought were positive, what were actually negative. So this gives a percentage of all of the negatives. What is the percent that we're actually correctly classifying as negative? I think by this point we see the pattern of how to implement them, so I'm just going to paste it in to find true negative rate, or specificity, by true negatives divided by true negatives plus false positives. We will see a true negative rate of very, very high, 99.9% again. So the problem with our classification model is about predicting the positives. So this metric is about the negatives that we got right. We could of course get that opposite fraction there to make them add up to 1, which is called the false positive rate, by the same thing as the above, except we flip true negatives to be false positives, and the denominator stays the same so that these two things would add up to 1. We would of course implement it just like this, changing true negatives to false positives. This is very, very small. This is very, very big. These two would add up to 1. Now, for those 4 metrics we saw previously, it was all about the denominator being all of the actually observed classes. This is all of the actually negatives. This is also all of actually the negatives. This is all of actually the positives. And again, this is all of actually the positives. Now what we do with something called precision is we change the denominator to this, where we have precision, which is also called the positive predictive value, where the denominator is the true positives plus the false positives. This is not all of the actually positives. This is all of the predicted positives. And we take this as a percentage of, hey, all of the stuff we predicted positive, what was actually positive? Following the same pattern, we implement this as PPV is equal to the true positives divided by the true positives plus false positives. We call that and see that we have a precision of 71%. It's okay, but definitely could use a lot of work. This metric was all about the positives. There's of course something analogous for the negatives, and we call this the negative predictive value, where it's true negatives over true negatives plus false negatives, meaning of all of the things that we predicted as negative, what actually were negative. NPV is simply Tn over Tn plus Fn, 99.9% again. Of all the things that we claimed were negative, pretty much all of them actually were negative. Now let's remember the context of our problem for these two metrics. Negative means not fraud, and positive means fraud. So this number here means of all of the things that we thought were fraud, we predicted these ones as fraud, we're actually only right 71% of the time. And here, if we predicted it as a negative, we actually are right 99.9% of the time. Now those metrics are great at showing us exactly what we need to do to improve, but we also need a bunch of metrics that in general show show that our model is pretty good or pretty bad, because they're a little bit tough to interpret sometimes. So this thing called balanced accuracy is a really good way to show how good your model is at predicting both classes. True positive rate plus true negative rate divided by 2. It is simply calculate the true positive rate of all of the positives, what are actually predicted as positives, and of all the negatives, what are actually predicted as negatives. You take both of those numbers and you average them to produce one number. We define balanced accuracy and we calculate the true positive rate, which is that, the true negative rate, which is that, and we simply return the average of those two things. Now, if we calculate this metric, we will see that it is 77.7%. That makes a lot of sense because it says, yeah, it's pretty good. One of these two things is very good and the other is only okay. 77% is a much better accuracy measure than 99%, which the general accuracy metric gave. 99 says we're really, really good, but we're not. Balance the accuracy and it's actually only like 77%. Now, it's worth noting that accuracy is not always an unreliable metric. Balanced accuracy will always be good, but accuracy itself is only sometimes good. If we put all of the trues in the top and everything in the bottom, it's only going to be a meaningful metric if the classes are what we call balanced, and this is not balanced at all. Another metric that's more commonly seen than balanced accuracy but serves a pretty similar purpose is called the F1 score, and it looks slightly more complicated. It's 2 times precision times recall divided by precision plus recall, but it's actually still a number between 0 and 1, where 0 means we're not predicting very well at all, and 1 means we're predicting very, very well. Technically, it's the harmonic mean between precision and recall, but it's still some sort of combination between looking at both classes individually and not grouping them together and making an unreliable metric, which is the accuracy. Define F1, which takes all of those things. We'll calculate the precision, which I called the PPV for the positive predictive value. We get the recall, which is the true positive rate, and we simply return 2 times precision times recall divided by precision plus recall. If we output that, we will see an F1 score of 0.625, pretty similar to the 77 value, somewhere in the middle, saying we need improvement in one of the two areas. Now, what you may or may not know about our logistic regression model, it actually outputs probabilities. We get those by model.predict proba. That's the function that gets the probabilities of it being fraud. And so if it's 60% chance, well, then we have a 60% chance that it's fraud. And if it's 0.3, we have a 30% chance that it's fraud and a 70% chance that it is not fraud. Pass that X test, and then we have to get all the rows, but only the second column like that. We will see that the majority of them are very, very close to 0. That is again because the model really thinks that most of them are not fraud, and that's probably true. The majority of them are not fraud. If we take this probabilities vector that we just created and we do greater than 0.5. What that does is converts all of the values. If they're less than or equal to 0.5 or 50%, it'll say false, which really means not fraud. And if they're bigger than 0.5, it'll assume that it is fraud. We can look at the distribution of this with a pd.value counts, and we see the distribution that almost all of them are false, meaning those were all not frauds, and these 28 were predicted as fraud. Now, it turns out that you can change this distribution very easily by changing this value, which is called the threshold. If we raise it, notice what we're going to see here is that true goes from 28 down to 23, and this value would have gone bigger. And if we make it even bigger, if we make this say 0.8, well, then we're going to get less and less trues, and we're going to get more falses. We could also go the other direction and change this to 0.4. We're going to see even more trues, and as we go lower and lower, we're going to predict much more of them as trues. We can pick any threshold value right here between 0 and 1 to make our decision boundary. In general, still with prediction, we do use 0.5 because it makes the most logical sense and is generally the most accurate. I'm going to use NumPy to generate 2,000 different thresholds that are evenly spaced between 0 and 1. With import NumPy as NP, and then set thresholds equal to the np.linspace between 0 and 1, and we get number of them equal to 2,000. I'm going to make them a little bit smaller and do as type np.float16, and then I'll just output thresholds right here. Now, we saw that as we change the threshold, the corresponding distribution would change given probabilities is greater than that threshold. What I want to do is, given all of those 2,000 thresholds, I want to generate the distribution according to that threshold. So we'll make this variable called all predictions, and we'll set that equal to the numpy.array of the list where we do probabilities, because those probabilities aren't going to change. It's just what we're going to do with them. So we'll do brackets of probabilities is greater than t, and then we'll do .as type an integer instead of the trues and falses for t in thresholds. Given all the thresholds, let's loop through those and calculate probabilities is greater than t, not the value counts, but just this vector right here, given that specific threshold. The all predictions.shape, 2000 rows by 22,785 columns, so 2,000 thresholds, and these are all the different values. If we look at one of them, so all predictions sub 0, corresponding to what will actually be this 0 threshold. Well, they better all be 1s because we're giving absolutely no chance for it to be predicted as negative. If we give it a little bit of leeway, you will start seeing some negative values. -1 means given the final threshold, which is just 1. This is the other extreme. All of them are going to be not fraud because we're giving it no chance to be predicted anything other than not fraud. Now, for all of the metrics that we looked at above, like accuracy, precision, recall, and so on, given these different distributions or given a different threshold, you can calculate each of those different metrics you want, and they might be different given a different threshold. The one that was used above and is most common was the threshold of 0.5. To make a new metric that's very commonly used, I want to calculate all of the different true positive rates and all of the different false positive rates for each of the different thresholds. That'll make sense shortly why we chose true positive rates and false positive rates. Now, the code for this is a little confusing, so I'm just going to paste it all in and explain it all at once. What we have here is confusion matrices. So before, we only had one confusion matrix because that threshold was at 0.5. But now for every single threshold, for all the prediction vectors in all of predictions, so we go through for each of the thresholds, we get our predictions vector. Then we can get the confusion matrix for each of those, comparing it to the actual observations. Then, since we have a confusion matrix for every single different threshold, we can get the true negatives, false positives, false negatives, and true positives for each of those thresholds. After that, we're able to calculate the true positive rates and the false positive rates given all of those different TN, FP, FN, TPs. If that didn't make complete sense, don't worry, it just matters that we're getting a confusion matrix for each of the thresholds, and we're getting the true positive rates and false positive rates for each of those thresholds. Now we're finally able to draw what we call the ROC curve, and we're going to do that using Plotly to easily show the color. Import plotly.express as px, and we're going to do px.scatter, so a scatter plot, where we set x equal to the FPRs, so we're putting the false positive rates on the x-axis, and we're going to put on the y-axis the true positive rates, color equal to the thresholds. Just to make the graph look a little better, I'm going to paste in a couple different labels. If we plot this thing, we will see the following curve. We just implemented a very, very famous metric, which is called the ROC curve. It shows over all possible thresholds between 0 and 1 what the false positive rate and true positive rate is for that threshold. And so here, if you hover over it, we will see threshold. And as we go over here, the threshold is increasing. We go over here, the threshold is decreasing. The color shows that as well. A completely ideal and perfect model according to this graph would have all points over here. And that is because we want a high true positive rate. It's really a measure of false negatives, so it would mean we would have very few false negatives, and a false positive rate, well, we don't want to have that. We want to have a very low false positive rate, so we want it to be as far left and far up as possible. Low false negatives and low false positives. Unfortunately, most curves actually look just like this or something similar, instead of all points being in the top left at 1 and 0. So notice that as we go up and around like this, the threshold is decreasing. We can see that by the color. So all the way, if we go to the extreme right here, the threshold is 0. That means we're going to predict every single thing as positive. Hence, no wonder the true positive rate is 1, because that means of all of the things that were actually positive, how many did we correctly classify as positive? Well, we classified every single instance as positive, so yeah, it's going to be 1. But we are going to have a very big problem with false positives. We have a big, in fact, maximum false positive rate because of all of those negative examples that were actually negatives, we predicted them as positives. So we do not like this point. We need to find a balance over here. So if we start to increase the threshold a bit, it gets more and more likely that we predict examples as negatives. Okay, and in fact, if we go all the way down here to where we predict everything as negative, because the threshold is 1, the probability can't possibly be bigger than 1, every single instance will be predicted as a negative. It has pretty much the opposite problem as this point over here, because yeah, the false positive rate will be 0. we're predicting every single instance as negative. We won't have any times where we predict that something is positive, but it's actually a negative, because we're not predicting anything as positive. We're predicting everything as negative. Except that doesn't mean that the true positive rate is still good. It'll be terrible because we predicted negative every single time. And so of all the positives, we got all of those wrong. So we need to find some balance in the middle here, threshold, and we want the point that's at the top left over here. Note that we can't actually just take this threshold and choose that, as really that's just going to what we call overfit the test set. This is what shows the metric itself, and the curve is always going to look something like this. Now this graph by itself isn't really a metric. We can turn it into a metric very easily. Scikit-Learn.metrics, we will import AUC, and we will do the AUC of the false positive rates and the true positive rates, the x-axis and the y-axis. If we take the area under the curve of this graph, well, it's going to be between 0 and 1, like all of our other metrics, and we get 0.98. Note that that's a really good value, and it's saying that AUC is really, really good for this, and it's supposed to be a metric that accurately balances both. That's why you really have to look at a bunch of these different metrics, including balanced accuracy, F1 score, and all the individual ones to really make an informed decision about your model. There's two things we really need to cover before you go. One is called the classification report from Scikit-Learn. From sklearn.metrics, import classification report, and we call that with our observed observations, our test predictions, set those labels to be 0 and 1, and this is again what we want to call these things. We can see a classification report, and it shows the precision, recall, F1 score, and support is just the amount of examples that we had. Note that how do we have precision and recall for both of the different classes? Well, that's by basically assuming that this is the positive class, this is the precision, this is the recall, this is the F1, and for fraud, this is assuming that is the positive class, this is the precision, this is the recall, this is the F1. So what a really good thing to do is we take the what we call macro average, the averages of these things. So assuming this is the positive class, get the precision, assuming this is the positive class, I get the precision, and we take the average of those. When we take these averages, it's a really good way to look at all of the different distributions of the classes, and if there's more than one class, which we'll look at next time, then this is a really good way to do that. The final thing is implementing this thing called Matthews correlation coefficient, which is something that for some reason barely anybody knows about, but is extremely useful to accurately measure the score of your classifier. All you need to know here is a bunch of different combinations of the true positives, false positives, and all that stuff. And it gives a very reliable metric, which in practice is generally only between 0 and 1. You may see it between -1 and 1 if you did something wrong, but the bigger it is, closer to 1, the better your model is. The closer to 0, the worse your model is. And this is a very reliable metric, regardless of the balance issue. So you see here, only 36, 22,749. It is still a very valid metric. It is easy to implement this, and actually, I want you to do that by yourself if you feel up to it. I hope you enjoyed this. Definitely subscribe if you're not already, and good job, because you've learned a lot if you got through this. It is extremely helpful.